All right. We got slope fields today. No Euler's method if you are taking the BC test. Who's taking the BC test? Anyone? Anyone sign up for the BC test on purpose? All right. So we're not going to worry about Euler's method. All right. What do you know? Quick little facts. You guys know about Euler, right? What do we know about Euler? Main thing you think of. Bless you. The letter E comes from Euler. 2.718. The natural number E comes from Euler. Euler's number. All right. So we're going to talk about differential equations, which I tell you what, we tend to cycle through things so that it's not like a big shock value when we go to do it in a section. We try to draw it all together as much as we can. So differential equations are just a fancy name for the derivative of something else. Now, slope fields, I will say, are a newer topic. By newer, I'm talking, now I'm old, but newer is like I didn't learn it when I was in high school or college. So post 2001, 2004, 5, whatever is when I graduated from college. Like it's from then till now. So it's kind of a neat, interesting application of derivatives. So a differential equation, something you want to write down. An equation involving a derivative is called a differential equation, and the order of a differential equation is the order of the highest derivative involved. So an acceleration function would be a second order differential equation. Chemistry people might be having some thoughts go through their head about orders. Yes? No? First order, radioactive decay. Yes. We'll talk about it. Did you?
It was our worst test ever.
Oh, wonderful. This is going to be a very popular FRQ question. Like this is one I would say I see on 70% of the past tests they've released. I've seen some sort of differential equation with a slope field. They like to pair these together with a part A being a slope field, which we'll talk about today. And then parts B and C. We'll talk about a little bit of those today, but we really won't hit that until section 6.4. Solving what's called a separable differential equation. Ready? We got baby steps today. Now, the directions are mainly the only really challenging thing about this problem. Find all functions y that satisfy dy dx equals 3x squared plus cosine x. I'm not going to give you any more information than that. Ready, set, go. That's a 3x squared plus cosine x. Any takers? Hi, Avery. Any takers? Cool.
X cubed plus sine x plus c.
Very nice. We call that the antiderivative. I kind of feel like mean saying this, but I will enjoy counting off points if you forget plus c. Okay. Because I've warned you. Some of you are still forgetting it, and I let it slide on this last test. I'm going to bring the hammer down on this next one. Shots fired. I've warned you. What did I say? Do you remember why I said don't forget the plus c? Because when we're doing area, did it hurt you? No, because capital F of 2 minus capital F of 1. Oh, look, plus C minus C. They always canceled. Area, number. Antiderivatives. Ooh, buddy. It's going to hurt if you forget it, especially in section 6.4. All right, we'll talk about that later. Now, why did they say find all functions? Well, isn't this, what does the plus C do to it? The plus C keeps the same shape, but what does it do to it? Plus a constant. Doesn't it vertically translate the graph of x cubed plus sine of x up and down? Ready? Big idea for today. What are the slopes at any x? What are the slopes of this function? Oh, they're 3x squared plus cosine x. Ready? Won't this graph right here, when x is pi, have the same slope on every vertical translation of that graph? Let me say it again. Won't the slopes at pi, the slopes of this graph, it's every vertical translation possible, but aren't all the slopes the same vertically? They don't have the same y value, but they have the same slopes. Big idea. Got it? So, if the general solution to a first order differential equation is continuous, the only additional information needed to find a unique solution is a value of the function at a single point called an initial condition. So I don't know that you need to write down all of this. Here's what I will say. Here's what we've learned so far. Are you ready? If I wanted to find what's called a unique solution, don't make it too complicated. All that means is you solve for C and you have an exact number for C and you know exactly which function you're talking about. So if I were to solve for C here, what do I need? A point, an x and a y. Oh, that's all they're saying. The only additional information needed to find a unique solution is the value of the function at a point, called the initial condition, which they told us before. Let f of 0 equal 7. Okay, now we can solve for C. And a differential equation with an initial condition is called an initial value problem. So these are called initial value problems. We've already solved some of them. All right, where we have found the antiderivative with the C in it, plugged in x and y, solve for C, plug it back in, and get our particular solution. Particular solution is the f of x. I'll call it f of x. It could be whatever. With C plugged in. I would mainly suggest, if you're going to not write all this down, which is fine, write down the main terms, because in the FRQs you're going to see, they're going to use this exact vocabulary. Initial condition, particular solution, initial value problem. Initial condition, particular solution, initial value problem. That's how they ask the question on the AP test. They'll say, find the particular solution to the separable differential equation below. So the more familiar you are with this vocab, the more you'll be, oh yeah, that's that process we did. So we kind of narrowed our scope of antiderivatives to what? Polynomials, so power functions, even with fractional powers. Then we had trig functions. We had some E functions. This chapter, we're going to unveil all the antiderivative rules, okay? We'll practice all of those. Yes, a lot of LNs, a lot of E's, along with some other antiderivative rules. Are we good? Good? All right. All right. So let's say we want to solve this initial value problem. I think this was number 12. And I think I might have even assigned that for homework, did I? Yep, that's gonna be your last one. So we're actually gonna do this homework problem together. So the directions would say solve the initial value problem explicitly. So what that means is find the value for C, plug it back in, give me the exact particular solution. Not just the family of functions with the plus C in it. Solve for C as well. All right, so we're going up a layer. We're doing an antiderivative. So we have y equals, what's the antiderivative of 2e to the x? 2e to the x. It's a constant multiple rule. 2 goes along for the ride. E to the x's derivative is e to the x, so the antiderivative of e to the x is e to the x. All right. What's the next term going to be? Plus sine of x or minus sine of x? I hear minus. Let's try it. And this is where I get a little disappointed. Is I had you memorize all of those rules again so that we weren't like uncomfortable with them. And then you guys, I don't know if you weren't checking them or you didn't remember how to check, but this gets checked with a derivative. What's the derivative of sine of x? Cosine of x. So the minus goes along for the ride. The derivative of minus sine of x would be minus cosine of x, wouldn't it? So I feel good about that. What's in red is good. All right. And then plug in 0, 3 to solve for C. 3 equals 2e to the 0 minus sine of 0 plus a constant. What's e to the 0? Good, 1. 2 times 1, 2. Minus sine of 0. You should not have to stop and think about that. What's sine of 0? 0. 2 minus 0 plus c. Subtract 2. C equals, careful, 1. So my particular solution is y equals 2e to the x minus sine of x plus 1. That would be my final answer, that particular solution to the initial value problem. And what was the initial value? Practice our vocab. 0, 3 was our initial value. So that's all a differential equation is. Okay, we've been working with it. We just maybe haven't used that expression before. All right, now a quick little review. To ln or not to ln? Ooh, this is fun. It's like a game. That is the question mark. All right. 1 over x is antiderivative. ln Thank you. ln absolute value x plus c. We talked about why the absolute value. Do you remember? When we're going backwards, the domain of the original had to match the domain of the derivative. And if 1 over x is the derivative, what's 1 over x's domain? All real except for 0. I go up a layer. The derivative of this thing had to be all real except for 0. Uh-oh. ln's domain is greater than 0. Slap an absolute value on there. They match. So that is the correct antiderivative. Make sure you put absolute value. They like to test that. So first one, to ln or not to ln? To ln. Next one. To ln or not to ln? That is the question. Give me a little head nod or a shake. That's cheating. No bobbleheads here. Are bobbleheads still a thing? Don't be lazy. How could you check it? Let's say we test it. Ready? 2ln. How can we test it? Take the derivative. FTC part 1. What's the derivative of ln of u? 1 over u times u dx. And du dx of this would be 1. Do we get back to where we started? Yes. 2ln. I feel like I cheated that check mark a little bit. Needs to be less differentiable. All right. In blue. 2ln or not 2ln? Jackson, I appreciate how hard you think about this. He's got the chin scratch going and everything. That's when you know either he's really thinking or he's trying to sell it while he's daydreaming. We've all been there. You know, like you're daydreaming about like, I got a really good lunch today, but he said something about derivative. I just went, yeah. 2ln? Let's test it. Test it. What's the derivative of this? 1 over 3x minus 2 times 3. Now it's good. Isn't it? Oh, that's not dirty. That's beautiful. I forgot to mark Tyler absent. I was waiting for him to answer something like that. Have you guys seen Tyler today? Tyler, if you're listening to this, we miss you.
Keep on watching. I'll put money on that.
Who's loving this game so far? Yeah? Yeah. It's good stuff. Ready for the next one? What was I trying to do? What was I trying to do there? Did it bother you? 2ln or not 2ln?
2ln.
Times 2.
Now here's what I would say. Okay, get the root of the problem. Like you know the root of the problem is 1 over 2x plus 1. All right. So what's the derivative of this? 1 over 2x plus 1 times 2. The derivative of this is 1 over 2x plus 1 times 2. That's not that. I need to multiply this times 2 to make it work. And I get 4 over 2x plus 1. 2ln. So what is moral of the story? Every antiderivative is ln. Ever. No. Not true.
No way.
Well, yeah, if you put a 1 over 2x. Yeah.
Oh, yeah.
Or 3 over 2x.
2x.
Hey. Hey. Ellen. Ellen.
Hasn't failed yet.
Ah. Ah. Downloaded Minecraft on the Switch for my son a couple days ago. I missed those villager sounds. So.
Did you get the case tomorrow?
Got the. I didn't get like the protected. I got like the carrying case, but not like a protected case. Mario Kart's coming tonight, so I'm excited. All right. Now, I guess you could say the 3 is going to go along for the ride, right? Now, do we need to adjust this? Let's check it. Are you ready? 1 over u times 2x. So that's 6x over x squared minus 1. Yay? Nay? Or yay, but not yet? Oh, so what would I do? Divide by what? On what? I think we all agree we don't want that 2x there. Right? So what would I do to this, this thing up here? Okay, so put over 2x. All right, let's check it. How do I check this? How do I check this? Quotient rule. I'll take that as excitement. It does not work. Not 2ln. That doesn't work. It's going to have a different antiderivative rule. Not ln. Next one. Oh, there's more. This is getting spicy. I had fun making this game for you. Amy, this is going to totally mess you up for the test. I'm just kidding.
No way.
What do you guys think?
No.
Not 2ln. It's not a method we know yet. So wait, let's take a little pause here. Let's find a pattern. For those of you who just love the 2ln problems, right? What is the format you're looking for? What's the general template that will work where the antiderivative of the integrand would be ln absolute value stuff? If the integrand is 1 over or a number over, but what kind of stuff? Because this was stuff and it didn't work. What kind of stuff? Linear, something linear. I'm not even going to say x because we had a 3x here and it still worked because the derivative was just a number that we could adjust for. Does everybody understand when I say adjust for? Okay, the chain rule, we have to cancel that out, and we were able to. But if you have a squared down here, cubed, 1/2 power, it's going to end up having a chain rule that's another x term, and then you're going to have a quotient rule to check it, and it's just not going to work. Let me say it again. The 2ln we're looking for number over a linear expression. Okay, linear. 5x minus 10, 3x minus 2, 2x plus 1. Those are all fine. And dandy. All right? But what about something like that? Well, it didn't really follow our rule. So if you're already saying no, then let's find the antiderivative of this. Go for it. Go. Those of you who are resisting to pick up a pencil, now's your time. And just remember, you can always check it. Just for a little bit of inspiration for the day. Quiet, please. Quiet, please. Listen. Wow. We're done.
When do we get them?
When do you guys want them?
Today.
Wow. For a bunch of group of kids that are resistant to picking up pencils, what do you think gives you the right to pick up a calculator? It snaps like that.
Mine continues to die.
That's fair enough.
Mine's definitely
All right. First of all, 2ln. Wendy said no, so I trust Wendy. 2ln? Ooh, I hear now 2ln. ln, absolute value e to the x. Let's check. What's the derivative? 1 over u times.
Oh my god.
Wait a minute. Yeah, that's just 1. That's not that. Not 2ln. You know what? That one wanted a different color. We'll give it a different color. So let's keep trying. Let's keep trying. Any ideas? So you're saying 1 over e to the x times ln absolute value e to the x? That'd be a quotient rule. Any ideas? This was actually not that hard. You guys got this. You got this. What's the first rule of antiderivatives? Do I know that one? Do I know whose derivative this is? No. So try something else. Madison.
1 over e to the x can be rewritten as
E to the negative x. Now, I had not done any calculus yet. Madison just rewrote it using exponent rules. Now, we know the derivative of e to the x is e to the x. So, isn't it going to have some version of e to the negative x in it? Check it. How do we check it? Take a derivative. What's the derivative of e to the negative x? E to the negative x times. Do you see a negative 1? So what can I do? Beautiful. Beautiful. All right. We're going to hold off on that for a second. No, you guys need that. You need this. You need this. Everybody wave to the people looking. You know why Mr. Hale came in.
Yes, I did. To see the calculator in action or what?
He wants to hear it again.
Is this calculus?
They pretend to be.
They don't look smart. Let's get that out of the way right away.
All right, let's give him the full experience. Brand new calculators. Just listen.
We got a couple visitors from Maslin. Right? They just came to see. They came to see our calculus class.
What do you guys teach?
Language arts. I'm seventh grade.
Welcome. Ready? They love it. These are how this is how nerdy they are.
I tell you, no, you gotta listen for the click. That's a key.
They're gonna get up tonight. They're gonna go home tonight. They're gonna be like, I'm frustrated and stressed out. One who's like, I just need.
Just keep that in mind when you take the AP test. I mean, if some of you are, if you take the AP test, that's the key, right?
All about the click.
Yeah. You got to time it properly. Okay. Okay. Everybody except Wendy, have a good day.
Bye, Mr. Harold. Bye. There's a couple people in here that would like go crazy if they heard clicking and turned all over. Right, Madison? Oh, Madison. All right. Other people. Who are the other people too? Yeah, Caden. We all have different personality types. Tyler's like, he'd be like, I need more click.
Constant claims.
Yeah. All right. Go ahead and find the particular solution now that our distractions. He's probably so embarrassed to like bring him back. Like, oh, he probably walks around telling them, oh, you know what? These garage doors aren't a distraction at all. We'll walk right by these students and they won't even look. And then I'm out there. Why do I stop at jail? What's that, Lizzie? Trying to get me fired?
Yeah.
I can't fire you.
Yeah.
I could sub and Camping City. If I got fired, they pay pretty good down there for subs.
Wonder why.
Oh, this is all being recorded. How much do they pay? Like $250 a day, like $225.
Are you kidding?
Because they can't find it.
You gotta have teacher's license?
No, just have a degree,
That's it.
college degree. So here's my plan for the rest of the year. If I'm out, I only get a couple days vacation, so I can't really take vacation. I'll just take sick days. Okay. Take sick days, go down there and sub.
Jesus.
He got that recorded too.
When were you taking notes? Should be.
So you don't see me for the rest of the year. Where did Mr. Russell go? Got calculators. Yeah, I just was outlining too much. But if I'm sick, I can get paid here.
That's really smart.
I'm gonna delete this whole section of the video. All right, let's check the antiderivative first. What's the antiderivative of e to the 2x? Good, 1/2 e to the 2x minus 3/2 x squared plus a constant. That's called the family of functions. That's the antiderivative, right? But we're asked to find a particular solution. So let's plug in 1/2 and 1/2 for y. One for x. Now this one's kind of ugly, but let's see, add 3/2, 1/2, and 3/2 is 4/2, which is 2. So we get c is 2 minus 1/2 e squared. Is that what you guys got for c? Which is a little bit ugly, but it's okay. It's a number 2. And if you're ever in doubt, you can always take the derivative of that, make sure that it matches up with the original. Oh, it's not bad. Ready? What's e to the 2x's derivative? E to the 2x times 2. That 2 and that 1/2 cancel, so e to the 2x. Good. Next term, power rule, 2 times 3/2. 3, so minus 3x. Good. 0, 0. Those are numbers. Derivatives are 0, right? Don't let that bother you. E squared is a number. The derivative is 0. Does it match? Yes. Does it go through the point you want it to? Yes. That is called the particular solution. All right. Yeah, let's do it. Let's do it. This is good practice. Next one. I really was hoping to get to slope fields. We'll see. We might get to it at the end of class today. Oh, yeah, there's going to be homework. You gotta use those new calculators if we get a chance. Mario Kart out for delivery. It's 15 to 3:15.
Buy it like on the Nintendo store.
Could I have?
Yeah.
I could have. Here's the problem. Did I tell you about the whole story about me downloading the game?
No.
I'm in the works of getting internet at our house. We use our phones for everything. We have unlimited data. Did I tell you this?
No, but it makes sense.
So I was going to download the game. So I bought a 256 gigabyte micro SD card. Okay. So because they wanted NBA 2K22. So I started downloading it, and it said, "No, your Wi-Fi stinks. Stop downloading this game. Stop downloading this game. Why did you even think you could?" All right. It was like 42 gig. All right. So I went. This was last weekend. Memory card comes. They're all excited. We can download the game. I was like, well, we can't download at our house. Like, let's go to the school. So we're here on the weekend. Did I tell you this story?
No.
And I'm like, it's going to be a while. I should probably take something to entertain them. And so I brought a mini basketball hoop. We put it up on my door facing the outside. We're doing trick shots for a couple hours. I hope they don't watch the footage out of that camera. So it took a couple hours, still wasn't downloaded. I'm like, nobody's here on the weekend. The internet speed should be pretty good. Didn't download for a while. We had people coming over for dinner that night. So we went back home, left the Switch here, locked up, still downloading. I came back later in the night, still wasn't done. So my brother lives over in Heritage Glen, I think it's called. And he's got really fast internet. I was like, hey, can I come over and just finish this game? He's like, yeah. Whenever they finished it up, I'm like, this is not sustainable. I can't keep doing this. So we're now buying just the cartridges until we can get real internet.
When are you getting real internet?
I went to Verizon yesterday. They've got like a home internet thing you can get. It's like 5G. So I'm gonna see if it's would work in my area. We'll see. I'm optimistic. Does anybody have that? Anybody have a Verizon home internet? Because I can't. I'm out in the middle of nowhere. Like I can't get DSL. We can't get like whatever they call it, AT&T, Uverse. Can't get any of that. There's another section of the video I'll have to delete. All right, antiderivative of 2x. Easy. Minus, you got this, tangent x plus a constant 3, 0. What's the tangent of 0? Sine of 0 to cosine of 0? 0. So C equals what? C is 3. So f of x is x squared minus tangent x plus 3. Good? Good? Beautiful. Beautiful. Now, slope fields. Okay, this is the topic I said was new, relatively new. Here's what it does. You don't have to write you can just write down slope. I would write down slope field for sure. If you want to write a little synopsis of it, that's fine. The differential equation gives the slope at any point. Ready? Derivative. Plug in an x, get out a slope. Plug in an x and y, get out a slope at that exact point. Isn't that what a derivative tells us? Right? So here's what I want you to imagine. Imagine every let's say I have dy dx equals 2x. Ready? What's the derivative at 0? When x is 0. When x is 1. When x is 2. What does that mean? At x equals 2, whatever the original function is, has a slope of, when x is 2, the original function has a slope of 4. But where? Well, when x is 2. What's x equals 2? When x is 2, the slopes are all 4. When x is 1, slopes are all. Why? Because it's every vertical translation of x squared, right? Isn't x squared plus c? What's x squared plus 1's slope at 2? 4. What's x squared plus 2's slope at 2? 4. You with me? So a slope field is going to give us the slope on, it's going to graph enough little tangent slopes that we get to picture what the original function would look like with the plus c's in it. Okay, it's easier to just show you. So here we go. There's what we have is dy dx equals 2x. Do you agree this red one right here is x squared? Y equals x squared. But just like I said, isn't x squared plus 1 a solution and x squared plus 2 a solution? If you were to only focus in at the integers are whole numbers. Ooh, that was almost too much. I'm going to go with it. Just draw little tangent segments. See all those red and blue little tangent segments? What are those representing? Slopes. If I graph enough slopes, like little tangent lines, little tangent segments, can't you start to picture what the original looks like? Let's say it again. If you graph enough little tangent slope segments at all the whole numbers, like 0, 1, 2, you start to picture what the original function looks like. Right? And we're not going to go as far as graphing at like -1/2. That's just tedious work. But if we graphed enough of these tangent segments, wouldn't you get the shape of the curve that's the antiderivative? That's the whole point. When would you ever use this? Well, if there's some function, this is not a good example. If there's some function that you don't know what the antiderivative is, let me say it again. There are some times when you don't know what the antiderivative is. It's okay if you are asked to draw a slope field. Maybe you don't know what the function is, but you can at least picture it. Does that make any sense? You might be able to at least picture it if you're asked to graph enough tangent slopes. That's the whole idea. So when you graph a slope field, all you're doing is sketching the slopes at the intervals they tell us. So this is 0. Let's call this pi over 2. Pi over 2. What's the cosine of pi over 2? Cosine of pi over 2? 0. So what am I doing? I'm graphing little tangent slopes of 0 vertically at pi over 2. Let's call this pi. What's cosine of pi? Good, -1. I'm going to dress up as a unit circle for Halloween. I just scare the living daylights out of you. All right. And if you graph enough of those, do you see how you're starting to visualize what function? What function has a slope of 1 at 0? Sine. It's the antiderivative of cosine of x. You're visualizing the antiderivative function. We're going to stop there for today. We got some homework for you. I don't know why I keep saying we. It's only me. Unless I have multiple personalities.
Devil on your shoulder that told you to give us homework.
Yeah. Yeah, we decided there's going to be this much homework. If you don't like it, blame him. All right, I like that. The ones I thought of before class. Day 1. And I apologize to anybody watching this video.